when I say short, sure, yeah, I understand totally what you mean. So when I say bin and remain formula, I mean Chandrasekhar's formula assuming Maxwellian velocity distribution. If you use this formula, this is very short, the time scale. Now Chandrasekhar's formula with the right distribution function only slow stars was this dashed line. Okay, and then if you include the fast, you make it even faster. I understand the short and fast confusion, but when I say the classic formula everybody uses in a paper is the class bin and remain that assumes the Maxwellian distribution. So this is very short and cannot explain the puzzle. So the initial motivation was this observational motivation, but of course this has, and we're working on implications and about Lisa at Northwestern with some students, so I think it's nice dynamically for these two. Smadar. Yeah, and I didn't mention it, and thank you so much for this, because I always forget for some reason, and I don't know why. So the reason in this is that if you don't take into account the stars around the secondary hole, then your black hole is going to stall at the effective radius of the galaxy, because you're not massive enough to segregate towards the influence radius. So it's a key, because the previous study that has looked at this didn't take into account this mass in stars around the secondary galaxy, and their satellites were stalling at the effective radius of the galaxy. So it's important because you have to continue the decay until you reach the influence radius of the galaxy. And this is also consistent with what Marta was showing before in some hydrodynamical simulations. It's a key to include this mass in stars. Yeah. You mean there exist galaxies that don't have? Yeah, because this is consistent with the study, because we don't say that if you look at the shallow, bright elliptical galaxy, you expect to see in all of them a second or multiple nuclei. This is an average number we calculate as a double averaging integral. It's just, we understand, you don't say that if I look at this galaxy, I will have to see this multiple nuclei, otherwise the model doesn't work. It is that it is an average number that you calculate as an average double integral. It's indicative of statistically probability what I have to see, if I expect in these systems to see or not a multiple nuclei. Thank you. No, this I have to take. Sorry.
No problem.
Okay, so now can you tell us about the eccentric for stars around supermassive black hole binary?
You can go in your jacket pocket too if you want. Yeah, it's fine. Take too much time for this. Just go here. Okay. Thank you.
Okay, thank you. First, I'd like to thank the organizers. It's my great pleasure to be here today to discuss the interactions between stars and supermassive black hole binaries. And you may notice some modification in the title of my talk. So yes, I'm going to talk about the stars surrounding supermassive black hole binaries, as well as the binary stars in our own center of galaxy around the Sagittarius A, the single supermassive black hole. So my main collaborators on this project include Smadar Nels, Idan Ginsberg, Betsy Coxis, and Avi Loeb. Cool. So let's start with the stars around the supermassive black hole binaries. As we just heard from the great talks earlier this afternoon, these supermassive black hole binaries are well understood originated from mergers between galaxies. And at large separations, the size of around a kiloparsec also, these supermassive black hole binaries can be detected directly from direct imaging, such as the X-ray image shown here, where the plus shows the location of the double nuclei. And at shorter separations, around the size about 1 kiloparsec or less, it's quite difficult to resolve these supermassive black hole binaries. And it has been proposed to use the spectral and photometric features based on the orbital velocity, capillary motion of these black hole binaries. And meanwhile, we can also probe the properties of the supermassive black hole binaries from the interactions between the stars and the black holes, as studied by Chen Xie and his collaborators, and also Seto and Isawa, where this perturbation from the companion supermassive black hole can excite eccentricity of the stars and enhance the tidal disruption rates. And this excitation of the eccentricity and enhancement of the tidal disruption rates links to the dominance of tidal disruption events found in the E+A galaxies, as discussed in Nick's talk yesterday. So it has been found that the Kozai-Lidov effects plays a dominant contribution in the enhancement of tidal disruption rates. And in this talk, we're going to focus on the effects of Kozai-Lidov oscillations to the stars around supermassive black hole binaries. As Smadar described nicely in her talk yesterday, the eccentric or the Kozai-Lidov oscillations applies to a system that involves a hierarchical triple, where two of the objects are very close to each other, and the third object is very far away. So here we're focusing on the stars that are closely separated from one of the supermassive black hole, where the other one is the faraway perturber. And this can be treated as the interaction of these two binary wires in the circular regime, as the inner wire is composed of the stellar orbit around the primary supermassive black hole, and the outer wire is the supermassive black hole orbit. And as they trade angular momentum, the eccentricity of the stars can be excited, and the pericenter distance got reduced, and the stars can be tidally disrupted. So the octuple Kozai-Lidov mechanism is very powerful. So I cannot resist speaking about the important consequences about octuple and eccentric Kozai-Lidov mechanism. So it was found when the outer orbit is eccentric, interesting effects occurs where the eccentricity of the inner orbit can oscillate, and it can even reach very close to unity. And also the inclination of the inner orbit can flip across 90 degrees relative to the outer orbit's orientation, and it can even flip from almost zero, almost coplanar configuration, by 180 degrees. So these are very drastic changes, drastic evolutions. And these effects have wide consequences for a wide range of astrophysical systems. As discussed yesterday in Smadar and Fabio Antonini's talk, it can enhance the merger rate of black hole binaries in the center of galaxy. And also, it can also explain the stellar spin and the planetary orbital misalignment detected for exoplanets. And many of you sitting here have made a great contribution to explain this spin of the misalignment. So now let's get back to the tidal disruption. Okay, so as we mentioned that as the eccentricity, as we mentioned that during these oscillations, the eccentricity can be excited to large values close to unity. And you can see the eccentricity, 1 minus eccentricity can reach around 1 minus 10 to minus 5 to minus 6. And this tells us that the pericenter distance can be greatly reduced to about 1/millionth of the semi-major axis. So this tells us that even if a star that starts with semi-major axis 1,000,000 times the standard tidal disruption radius, it still has the possibility to be tidally disrupted. So it's a very powerful mechanism to enhance the tidal disruption rate. However, we need to be very careful because this Kozai-Lidov oscillations is a circular resonance. So if there is fast precession in the resonant angle or the liberating angle, the resonance will be suppressed and eccentricity excitation will be suppressed. As shown in the figure here, where the left panel includes a faster Newtonian precession comparing to the Kozai-Lidov oscillation, 10% of the Kozai-Lidov oscillation timescale. And the blue line shows the case including the precession, and the green line shows the case not including the precession. So you can see that including the precession, the eccentricity excitation is entirely suppressed. And also, when the two timescales are comparable to each other, the amplitude of eccentricity can also be suppressed a little bit. Okay, so now back to stars in the galactic center. Their two precessions have timescales that can be similar or smaller than the Kozai-Lidov timescales, and that are the GR precession timescales and the Newtonian precession timescale. And the Newtonian precession timescale is due to the stellar system self-gravity. So how many stars are still influenced by the Kozai-Lidov oscillation, and what is its dependence on the system parameters? So let's first look at the dependence in the plane of the primary supermassive black hole mass and the secondary supermassive, or the companion supermassive black hole mass. And the color-coded is the number of stars that can still be influenced by Kozai-Lidov oscillations, where the Kozai timescale is shorter than these precession timescales. So briefly, we can see that there are more stars that can be affected by Kozai-Lidov oscillations when the perturbing, the companion mass, is more massive. And this makes sense intuitively because the perturbation will be stronger, so you expect the eccentricity caused by this perturbation is also larger. And this is very similar to what we saw earlier this afternoon in Mathar's talk, that the secondary supermassive black hole got stellar density profile got changed, influenced much more than the primary, more massive black hole. Okay, so how about the dependence on the black hole binary separations and black hole binary eccentricity? So here we show an array of these plots on the total number of stars that are affected for different black hole binary semi-major axis and black hole binary eccentricity. So we can find a sweet spot that a large number of stars are affected by Kozai-Lidov oscillations. That is around black hole separation of around 1 parsec and in a slightly eccentric orbit. Why? And this is because when the supermassive black hole binaries are farther apart, the perturbation is weaker, so the precession will dominate. And when they are closer to each other, or when the eccentricities are higher, less stars are included in this hierarchical configuration. So what is the tidal disruption rate responsible by these Kozai-Lidov oscillations? So to answer this question, we use the illustrative example where we simulate stars using test particles around the solar mass 10 to the 7 solar mass black hole perturbed by a 10 to the 8 solar mass black hole using the secular simulation. And we used 1,000 particles. So briefly, we find about 6% of the particles got tidally disrupted. About 70% of them got scattered away. And this is shown in the figure here, where the blue crosses shows the test particles, the stars, got scattered away. And the red dots are the ones that survived for this 1 billion year simulation. And open circles are the ones that got tidally disrupted. And the color shows the end time of these test particles. So you can see that a large number of the stars initially starts within the Hughes sphere of the primary supermassive black hole, got scattered away very quickly. And we can also see that more of the stars survive when the mutual inclination between the stellar orbit and the supermassive black hole orbit are nearly in the same plane, around 0 degrees or around 180 degrees. And more of the stars got scattered away if their mutual inclination is higher, around 90 degrees. And this tells us that the survived stars' density profile will look like a shape of a donut, where when they are largely inclined from the black hole binary orbit, the more of them got scattered away. And also normalizing the number of disrupted stars by the M-sigma relation and the Bunker-Wolf stellar density profile, we can calculate that the tidal disruption rate can reach around 10 to the minus 3 per year when the black hole reaches this distance. Okay, so now let's shift gears and look at binary stars in our own galactic center. So as we discussed yesterday, that these binary stars play very important roles in the dynamics of the galactic center in Sari's talk and Now's talk. And in fact, there are binary stars already detected in our own galaxy. There are 3 of them. The IRS16W and the E60 are the eclipsing binaries, and this IRS16 Northeast is a long period spectroscopic binary. And thanks to the beautiful work on the high-resolution observation of the galactic center, they are very well characterized orbits of the S stars. So we wonder whether these S stars could some of them be binaries, and what's the likelihood to detect these binaries if they are really binaries. So next, we are going to use SO2 as an example and see whether it can be a binary and what's the likelihood for them to eclipse. So first of all, we will remember from earlier this talk and also yesterday that Kozai-Lidov oscillations, this powerful mechanism here plays the devil. It can excite eccentricity of these stellar binaries and cause them to merge. So here we want to find a parameter space where the binaries could be stable. And we calculate the time scale for the Kozai-Lidov oscillation and the GR precession time scale to see what is the parameter space where the GR precession can save this stellar binary. And this is shown in the figure here. I can see that GR precession can suppress this eccentricity excitation when the semi-major axis is within around 0.1 AU, very short distances. And also at these short distances, the evaporation time scale of this stellar binary is very long. It's longer than the lifetime of the stars. So these binaries are quite stable for these high massive stars. Also, so this small number also tells us some good news about detecting this stellar binary. And that is, at these small separations, the orbital motion of the stars are quite large. So it's easier to detect the radial velocity motion of these stars. And also, when they're closely separated from each other, the probability for them to eclipse will also be increased, will also be higher. So from these simple geometrical arguments, one can find that eclipse probability equates to the sum of the stellar radii over the semi-major axis, assuming the stellar binary is in a circular orbit and the orientation of the stellar binary is isotropic. So following this expression, we can find the eclipse probability for SO2 around a semi-major axis of 0.1 AU, and the maximum eclipsing probability when the two stars are very close to each other at near their tidal disruption radius. And this maximum eclipse probability can reach up to 75%. Well, for the SO2, their radial velocity measurements for this system, as done by Chu and his collaborators from the UCLA Galactic Center group, that based on the 16 years of the radial velocity measurements, there was no radial velocity variation beyond the SO2 orbital motion found, as illustrated in this figure, which shows the upper limit on the amplitude of radial velocity variations induced by any possible stellar companions. And converting this to the stellar mass, Chu and his collaborators found that the maximum mass possible around SO2 is less than around 1 solar mass for a wide range of orbital periods, smaller if the separations are shorter. Please. Oh, thank you. Yeah, okay. So requiring that the radial velocity to be smaller than the 20 kilometers per second, we can see that the eclipsing probability drops to 0 as the Q values are larger than 0.06. And when the semi-major axis is around 0.1 AU. And this limit is even small for smaller Q values when the stars are closer to each other with faster orbital motion. And you may wonder, because when the stellar companion mass is becoming smaller, the size of star is also smaller. So the flux variations, the dimming during the eclipse is also becoming shallower. So talking to the experts in the UCLA Galactic Center group, Do and he's kindly shared with us that it requires a flux variation larger than 3% in order to have a 1 sigma detection of the eclipses. So adding this requirement, the eclipsing probability is further reduced because it requires a larger overlap of the stars to have these larger flux variations. And you can see that the eclipse probability drops to 0 when the Q value is smaller than 0.05. And eclipse probability is still around 20% for this fine-tuned Q value, around 0.05. And you may also wonder that the Kozai-Lidov oscillations is quite sensitive on the mutual inclination between the stellar orbit and the orbit around the Sagittarius A. So if the mutual inclination is smaller, it's still possible for the stellar binaries to survive even outside of this 0.1 AU. So next we study the eclipse probability as a function of the mutual inclination. So unfortunately, SO2 is largely inclined from the line of sight. So the eclipse probability is 0 if the mutual inclination is very small. And the eclipse probability is quite large only when the mutual inclination is near 90 degrees, mostly above 40 degrees, when eccentricity are more likely to be excited close to unity. And we also calculated eclipse probability for eccentric orbit, and the eclipse probability increases when the eccentricity increases, because at the pericenter, the two stars are closer to each other and more likely to eclipse. And this is also unfortunate because when the eccentricity are higher, the eccentricity is more likely to excite to very large values by the Kozai-Lidov oscillations. Okay, so now I'd like to summarize. So for SO2, based on the radial velocity measurements, the stellar companion is likely very small, and the detectable eclipse probability is around 20 to 30% for fine-tuned Q value about 0.05, and it is generally quite difficult to detect these eclipses. And for SO2. And for the tidal disruptions of stars around supermassive black hole binaries, the companion supermassive black hole binary can enhance the tidal disruption rates and to roughly 10 to the -2 per year for this system. And the final geometry of the stellar distribution is in the shape of a torus. Thank you.